Okay, let's start. So, good. Okay, so last time we started talking about how to represent operators in Fock space, which will be the main tool for our description of many-body quantum problems from now on. Okay, so let me just remind you the formalism. The idea is that we have a vacuum state, and we define a set of creation and annihilation operators for particles, A lambda dagger, where the annihilation operators annihilate the vacuum, and the creation operators create particles. Here, lambda, the set of lambdas are single particle quantum numbers, okay, and which is usually it's a complete basis of such states, and
why usually and not all the time?
No, actually, always. Yeah, it's some complete basis that is sufficient to describe the particular problem, and we saw that we can characterize any quantum state that has well-defined number of particles by a set of occupations, where the meaning of this expression is that you apply it's some product over lambdas of A dagger lambda to the power n lambda, and sorry, there is a normalization factor here, 1 over square root n lambda factorial A dagger lambda to the power n lambda acting on the vacuum. This is the general basis of states. So all the possible states of this form a complete basis for Fock space, and any wave function is a superposition of them. So we know how to characterize states, and the next question is how to characterize any physical operator. And with this, we have a complete set of tools where we start describing quantum problems and solve them, where our goal, as usual, is to solve a Schrödinger equation. Okay, you have some Hamiltonian, and you want to find its eigenstates, its ground state, and maybe time evolution, and anything you learn from basic quantum mechanics, but we want to do it for the many-body problem. Okay, so the next, and of course, let me write down here the rules of the game. So we have two types of quantum particles, identical particles, either bosons or fermions. We are denoting them with an index that we call zeta, and I'm writing this, and we leave it on the board for the rest of the lecture. So for bosons, you have commutators of A and A or A dagger for any lambda prime equals 0. And a lambda prime dagger is delta of lambda prime. And for fermions, we have exactly the same thing, but with the anti-commutators. Okay, so these are the basic algebra rules. Okay, very good. So let's try to leave it here for the rest of the lecture. And now we are going to discuss classification of operators that describe physical quantities. And just like we know from basic quantum mechanics, we want to be able to express any such operator in terms of combinations of the operators A and A dagger, because for these we have these algebra rules that allow us to compute what happens when the operator acts on any state. We know that they are raising and lowering the occupations, and then we can calculate any matrix element, any expectation value. Okay, so the first thing is how to write the operators in the first place in this language. Okay, so so I think this I can erase, and we start just what we started doing in the end of last week. One body operators. So these are the simplest ones because they are actually quantities that we are familiar with from our elementary quantum mechanics, right? What is a one-body operator? It's an operator that acts on each individual particle independently, okay? So usually we can write such operator as a sum over this is for n particles, O, we write it like this, okay? Rho, or let us write it as O, little o n, okay? So O(n) is an operator that acts on the particle n, okay? But the index n, because the particles are identical, it doesn't have a meaning, you know, it doesn't matter which index of the particle, but if we want to keep track of the specifics of a particular particle, for example, its position, its coordinate is Rn, so an operator little o(n) can be, for example, the coordinate, or the coordinate square, or the momentum, which also can be written as a gradient operator, okay? And it will be a gradient with respect to the coordinate of that particle. That's the first quantization representation that we want to abandon, okay? We want to abandon it because we see that in this Fock space representations, we don't really keep track of which particle is which because they are identical. That's the main thing. We cannot distinguish them. So therefore, all we need is some representation that gives us the same matrix element as we would get for the first quantization, okay? Okay, so to do that, let us choose a basis lambda such that this operator On will be diagonal in that basis. Okay, so remember, lambda is a basis of single particle states. Okay, these are the quantum numbers of the individual particles, and we define the creation and annihilation operators with respect to this basis. We can change a basis. We also know how to do that. But for convenience, let us start with the case where the basis lambda is chosen to diagonalize O. Okay? Therefore, if I'm acting with this operator on a state lambda, what is the state lambda? It's a state where I have only one particle and it occupies the state lambda. What is going to be the result of this operation? Because lambda is chosen to be the basis that diagonalizes this single body operator, the result will be O lambda, right? It's an eigenstate. Lambda is an eigenstate in that basis, and O of lambda is, let me write it here. So O of lambda is actually this. Okay, it's the diagonal matrix element, and we also have, since we chose it to be, we chose lambda deliberately such that it's that O(n) is diagonal. This equals delta of it equals O lambda delta lambda lambda prime. Okay? All right? So, for example, let's take an example. The energy, okay, the energy of a single particle. If we choose a basis such that lambda is the good quantum number, all the energies are going to be epsilon of lambda. This is the spectrum, and the expectation value of the energy in that state is just epsilon lambda. Okay? Okay, so we know that this is satisfied. Okay? Yes?
How do you know that there is such base? Like,
what do you mean? There is always such, right? There's
No.
always. Any single particle operator, O(n) is nothing but a single particle operator.
Yeah, but
Okay.
if I like take a dagger.
No, I'm talking now about, let's start from something we already know and accept. And the way I defined it here, it's the first quantization. It's a first quantization notation.
But even if it was a dagger, it would just be like the eigenvalue 0. It's not.
First of all, a dagger cannot. It's not a
Okay.
physical operator that does it. Exactly, that's right. It's not a Hermitian operator. Therefore, it cannot describe any physical. There are operators that can be some combinations of it that will give you an expectation value. But here I'm starting from a first quantization. Okay,
Yeah.
like coordinate, momentum, energy. Kinetic energy, spin, okay? Okay, so this is something we already know, and the thing is that this state lambda, we know also how to write it in second quantization. How will we write it in second quantization? It's just a lambda dagger acting on the vacuum, right? So this is something, this is just synonymous, okay? That's the same thing, okay? Okay, so what this equation tells us is that if I choose the correct representation for O1 in second quantization, it should reproduce the same result. Okay? Okay.
O1 does not refer to like.
O1 is, this is how I defined it. Okay, it's a sum over particles. It's just a name, and that's exactly the thing, because the particles are identical. So if we write them in first quantization, we keep track of the labels of the coordinates, for example, R1, R2, R3. But when you calculate an expectation value, and you calculate it in this particular basis that diagonalizes the operator, you just get the quantum number, right? The coordinate disappears. For example, if lambda was, if you look at the momentum operator, okay? So you can represent the momentum operator for each particle as a gradient with respect to the coordinate Rn. But this n index has no meaning, because after you compute its matrix, this matrix element will just give you h bar k, right? With k, the wave vector. Okay? All right, so, okay, so.
Which is a physical thing.
What?
Which is a physical thing.
Yes, yes. That's right. Now, let me ask you this. So, I already made a connection from first quantization, if you like, to second quantization here. But now, what happens if, what do I get if I apply this O1? And remember, O1 has the potential to act on many particles, except it gives you just an independent sum of the contributions. Now, what happens if I apply it on a state? Now I'm writing it as a Fock state, which has only one label, one non-zero occupation, and it's in the state lambda. Okay? Okay, so this is just a lambda dagger to the power n lambda acting on the vacuum. Okay? It's a state with not one, but n lambda identical particles. Now, what is the result of this? Without, without having to invoke second quantization, what will be the result? Because for each particle, operating with O1 gives you O lambda times the state. It's an eigenstate. Therefore, O1 is this state is also going to be an eigenstate of O1, right? What is the eigenvalue? The eigenvalue is O lambda times n lambda, because you are just counting how many such particles you have. Okay? Again, you just have n lambda identical particles with the same quantum number. So therefore, I know that this should give me n lambda times O lambda times the same thing. Okay? All right? Yes?
Okay. No,
All right.
but that doesn't it mean that they should be commutative?
What?
Like
Should what?
O1, like excuse me.
No, O is this.
Yeah, so O n, so theta
Yeah,
n.
but for each particle, it's like when you have a ideal gas. Okay, what is an ideal gas? the expression for the energy, for the Hamiltonian, is just the sum over all particles of kinetic energies, right? Now, when it acts on a state where all the particles are in the same quantum state, with wave vector k, let's say, right? And you just have n lambda identical particles with the same quantum number.
That I get, but the way you wrote it, it's you activate the O1. It seems that
No, I'm saying let's for the moment ignore this.
Okay.
Let's ignore it. It's just I'm telling you what is the definition of the state. Okay? The definition of the state is, of course, it cannot be fermions if n lambda is bigger than 1. So it's just a state where you have a state lambda, and it's occupied by n lambda particles, identical particles.
Shouldn't it be lambda in the
Well,
there n lambda? Yes.
no, it's the same state. Okay, it's
Yeah,
an eigenstate. Okay? Okay?
Simply the amount of time that theta ends works on.
Exactly,
Okay.
exactly. That's exactly right, right?
But what if we
It's
have more-
trivial. It's like in an idea. I'm reminding you of the ideal gas because this is something you used in StatMech. You didn't even ask questions, right? What did you do? You said that the total energy is capital N times the single particle energy. Okay? Actually, if you do it for fermions, then it's. But if it's the same quantum number, all particles are identical.
so
Okay.
if we have multiple states with multiple particles in each state, it will be like a summation of.
Exactly. That will be the next stage. That will be exactly. That's exactly right. It's exactly right. So, if you accept that, we can also say something more general, because what you want is that. So, if you act on a state that now is going to be more general, okay, with some occupations of different quantum states, okay. Clearly, when you act, so now among these capital N particles, I have n lambda 1 in state 1, n lambda 2 in state 2. Each of them independently gives you a result like this. So this will also be an eigenstate where the eigenvalue is now going to be a sum over I, where I runs over all the indices here. N lambda I times O lambda I, all that acting on exactly the same. Okay. All right? Okay. Very good. So we actually know what our operator O1, if we represent it now in second quantization, should reproduce exactly the same result. Okay? And once we have this, we can actually compute any matrix element, because any matrix element between one Fock state and another one with n primes is going to be just a sandwich of this with that other state, right? Right? Okay, good. So now let me tell you, I'll give you a guess of what is the right way to write this operator. And the way we'll do it is, first of all, I want to define number operator n lambda operator. Note that the hat means that it's an operator, is defined to be a lambda dagger, a lambda, which is something you have already seen for the harmonic oscillator, right? Okay. Now, why is this called a number operator?
Because it's given the number of particles.
Exactly. So if you act with it on a state that contains n lambda particles in a state lambda, it will just turn the eigenvalue n lambda times the state. How to see it? So first of all, let me write here the following commutator. Okay, what is this? And this is something you have seen already for the harmonic oscillator, but let's do it explicitly. So it's the commutator of a lambda dagger a lambda. Actually, let me be more general and put here a lambda prime. And I want to let's calculate this thing, okay? Now for that, we already know what is the commutator of a dagger, and a dagger, etc. But here we have three, okay? We have three operators, but there is a nice formula. Let me write it here on the side. So if I have the following commutator, A, B, and C, where A, B, and C are any operator, you can easily show that this is given by plus AC times B, okay? And in fact, you can also rewrite exactly the same thing. You can also write with anti-commutators, and it will give you plus, here let me just check that. Yeah, if you want to write it with anti-commutator, there is a minus sign. And where is my eraser? Minus AC B. Okay? So this is a useful formula that I suggest you to write somewhere handy, because it's very useful for doing calculations. You can easily see that for both bosons and fermions, the result of this will be the only contribution will come from the first term, and it will give me simply a lambda dagger times the delta of lambda prime. Right? You agree? Okay. Wonderful. So there is this formula, and there is generalization of that. Actually, let me just use this first. So because of that, if I'm looking at the following expression. Okay, let me so if I apply this number operator on the state lambda that contains only one particle at the state lambda, I get a lambda dagger, or actually let me just write it here, n lambda acting on a lambda dagger 0. Okay, so what is it going to be? If I write again n lambda as a dagger a, I see that I can use this commutator to write it as a lambda dagger plus something that exchanges the two, right? Right? I can, so this is just saying that this expression is actually n lambda a lambda dagger plus a lambda dagger and lambda. But when n lambda operator acts on the vacuum, I get 0, right? Because it has the annihilation operator on the right. And therefore, the result of this is just n lambda, now the quantum number, the occupation, times the same thing. Okay? So, the state lambda is an eigenstate of the number operator, which turns the number, sorry, so it's just, so this is just, as we learned from here, this is nothing but a lambda dagger acting on the vacuum, which is the state lambda. Okay, so if I apply the number operator on a single particle state, it just gives me the eigenvalue 1. Okay? Okay. So that's already good because it suggests that if I now have a one-body operator that I write as the number operator times O lambda, it will give me the correct eigenvalue when it acts on a single particle state. Okay? But we can do better than that. We can prove a more general formula. Is it okay if I erase this? And again, it all follows from this formula with some algebra, and I think you will have a homework exercise proving it. You can show that n lambda commutator with a lambda prime to the power n, or let me call it n lambda prime. This commutator is just n lambda times a lambda dagger to the power n lambda times a delta. Okay? This is an identity that can be easily proved. Let's assume that we proved it. And because of that, we can do exactly the same trick because if we now take n lambda and act with it on a general Fock state with occupations of the various quantum numbers. Okay, and let's be a bit more specific and assume that somewhere here we have lambda I, and this is lambda I. Okay, so now the index I is some particular lambda, and this is the number operator for the state lambda I, but I have also some finite occupation of all other states. So what happens if I act with it on the state with, first of all, you see that it commutes with all the n lambda except the one that is the same lambda, right? Because of this delta. So if I write this explicitly as a product of all the daggers acting on the vacuum, I can shuffle the number operator until I get the creation operators at the state lambda I. And then if I use this commutator, I see that I'm going to get just n lambda I, just the occupation, times the state. So it is exactly the same state multiplied by the occupation of this particular quantum number. Okay? Very good. So you'll see that already we have a very good recipe of how to write the one-body operator. And if I define O1 to be a sum over all lambdas of O lambda n lambda, notice that here O lambda is nothing but the diagonal matrix element or the eigenvalue of the single body operator in the basis lambda, and n lambda is this number operator. Okay? Now, what happens if I apply this form on an arbitrary Fock state? I get, you see, for each lambda, I'll just get O lambda times n lambda hat acting on the state. But n lambda acting on the state just gives me the eigenvalue n lambda, right? So we know that this acting on an arbitrary Fock state will just give me the same expression without the hat times okay, so in other words, all Fock states in our basis are eigenstates of this operator with eigenvalue that is nothing but the sum of a lambda of O lambda n lambda, where n lambdas are the occupations that appear here. Okay? And because we know that, we also know how to write the any matrix element of O1 between two different Fock states, right? Because when I act it on the right, it just gives me a sum over occupations times the eigenvalue. Okay, and then I'm left with an inner product of one Fock state and another. Okay, so therefore, what I actually proved to you is that this representation of O1, which I wrote it as an ansatz, as a guess, if you like. Okay, but we see that for arbitrary matrix element, it gives us the same thing that we would get from the first quantization representation. Okay, so therefore, we actually proved that it's an operator identity. We proved that some operator has the same matrix element in this basis. Okay, the same matrix elements. Okay, they're all the same. Then it's an operator identity, and that's the way we want to write it. Okay, but it's not the most general way to write it, because we chose here a basis lambda that is very special. It's a basis that diagonalizes O for a single particle. Okay, what if we want to change basis?
Like
We can change basis. We already learned how to do it. Okay, so let me remind you. How we did it. So we already saw that we can switch from a basis lambda to basis lambda twiddle by writing for the annihilation operator. We write the sum over lambda of let me see, lambda twiddle that's right. It's so. Okay, that's the relation. All right, and now if we take let's rewrite O1. And I'm changing the basis. Let me write it explicitly. It's a sum over lambda of O lambda, A lambda dagger, A lambda. Okay, but now I do a change of basis to some basis mu. Okay, and then I use this transformation for both the A and the A dagger. What you get here is then a more general expression that is a sum over mu of let's write it like this. It's mu O mu A mu A mu. Okay, and this is just a matrix element of that single body operator, single particle operator, in the other basis, which is not diagonal. Okay, so this is just a number. It's just a number, and you see, instead of a number operator, now we have an operator that destroys a particle at state mu and recreates it at the state mu. Okay? So if it's not diagonal, then it contains terms that where I change the state of the particle. Okay. For example, let's say that this basis mu nu describes lattice sites in a crystal. Okay. You can describe a tunneling process where a particle hops from site I to site J, and this operator will describe this process, and its contribution to the total single body operator will contain a matrix L. Okay? So what I wrote here is the more general the most general expression for a one-body operator. Okay? This is the form, and this is just a set of coefficients, complex in general, right? Because it's a matrix element of a single particle operator. And what we can say about this this form of operators is that it always contains one annihilation operator and one creation. Okay? And it sums over all possibilities for taking a particle, annihilating it, and creating it in a new state. Sometimes it will be the same state, in which case it will just be the number of operators. Okay? But it acts on a single particle. That's what I want to emphasize. Okay? It acts on a single particle and each particle individually. Okay? So this is the second quantization form of one-body operator. And here we see that all this derivation was, in a sense, if we only have one-body operators, maybe we can do without it, because we already know how to work in first quantization, right? You have a set of independent particles.
We don't have to deal with all the
What?
And we don't have to deal with all the particle swap symmetries also.
That's right. I mean, so exactly. So to do calculations with it, it's much simpler because, right? Because you don't have to write a wave function in a complicated form. All you need to know is what are the creation and annihilation operators are doing on the states, okay? And when there are two written in second quantization, okay? Okay, but now it also gives us a hint how will we write a two-body operator. What is a two-body operator? It's an operator that describes something that involves two particles that are interacting with each other. Okay? Namely, interactions. Okay? You have some forces between two particles, and then this interaction in general will involve two particles where due to the interaction both of them can change a state from one state to another. So if you just had to say a wild guess, what will be the form of a two-body operator in terms of the structure? Okay.
You summon the both particles.
Yes. So the summation. Notice the summation here is only over indices of quantum numbers, right?
Yeah, but through this summation.
Yeah.
With summation over a non-coupled creation and annihilation operators.
Right, but let me refine the question. How many A's and A daggers will you have in the expression? Four. I mean, two of each. Okay? We'll see how we get it, okay? But it's a good guess. Okay? Because you have to, this acts on one particle. We have to write something that acts on two. Okay? Okay, so So let's see how we're going to write a two-body operator, and I start from one particular, one single body operator that we already see here is the total number operator. Okay, what is the total number operator? Okay, so n lambda hat is an operator of particles at state lambda. But if lambda is a complete basis of single particle state, what will be the expression for the overall number operator of the particles?
Summation over all specific.
Exactly. So this will be just sum over lambda of n lambda, which is sum over lambda of a lambda dagger. This is the total number operator. And notice that here I chose the basis lambda to be some discrete index, okay? But we saw already that there are some quantum numbers that are characterized by a continuous variable, for example, the coordinate, right? And in that case, we can also define creation and annihilation operators, but we want to define them as fields, as not as a and a dagger. We called it psi and psi dagger, right? And so psi of R and psi dagger of R, they describe annihilation and creation of particle at exactly the point R, and because of that, because it's a continuous variable and you're looking at only one point, they have units, okay?
And it will be an integral.
Right? What?
And it will be an integral, not that far.
If you, yeah, so then, exactly, so then, if you want to write an expression for n in this basis, in the basis R, it will be an integral over R. So let me write it like this. It will be an integral over R of psi dagger R psi of R, right? But what is then the physical significance of this expression? Psi dagger of R psi of R is something that after you integrate gives you a number. So what is it? This is the density operator, right? It's a density. The total number, okay, if we let us for the moment forget about the heads, the total number is an integral over space of the density of particles. So, so the density operator is one very important single body operators that we want to keep track of. We can erase for now. Okay, so let me write it here. Density operator. Let us denote it by rho with a hat to represent that it's an operator. And it's given by this, okay? And once again, it's not a pure number, it has units. What are the units of density? It's 1 over volume, right? Because when you integrate it over the volume, you get a number. So this is a density operator. And that's an operator that has a physical meaning. If we compute its expectation value in a given state, we get the density of particles, right? It has a very clear physical meaning. Okay? Very good. Now, why am I mentioning this? Because now if I want to write a two-body interaction, a two-body operator, sorry, what I'm thinking of is an interaction, like Coulomb interaction between charged particles, for example, okay, or van der Waals interaction, it doesn't matter. And interaction that between two particles, and most of the fundamental forces are like this, right? I mean, you can have also three-body interactions and four-body, but these are usually not fundamental, if you like, okay? Although you can have them effectively, okay? If you're looking at inside the material, the particles can interact via more complex processes, but the basic, like the Coulomb interaction, the gravitation, let's forget because we don't know how to quantize it, so let's not go there. But most of the forces that you heard about are just between two particles, okay? Okay, so So in fact, there are various kinds of two-body operators, but the one that is most familiar, and that's the one I'm talking about now, is a density-density interaction, okay? So suppose you have two-point particles. Now, going back to classical physics, we have two-point particles, and there is some interaction potential that depends on the coordinates of the two particles, okay? And V here is a potential, it's some function of R1 and R2. Often we think of interactions that depend only on the distance, but it doesn't have to be, okay? Doesn't have to be. Let's write it most general, okay? Now, okay, so this just describes the potential energy for placing two particles, one at R1 and one at R2. Okay? But now I don't have just two particles, I have many particles, like in electrostatics. Okay? When you solve the electrostatics problem, you had many charged particles. So how do you get the total potential energy of the system? You remember? How does the total potential energy look like? And this is in general something I call a density-density interaction. You write V to be, there's a factor of half, not to count twice, and then you have an integral over R, an integral over R prime, where R prime is different from R. This is just to avoid self-interactions, okay? And then I have rho of R, rho of R prime, okay, you can make it a vector, and V of R and R prime. Right? This is the expression. Okay? Right? This is something I'm sure you've seen many times, right? So you have a system with many particles, and they are distributed in space with some densities, and for each choice of the coordinates, you have a contribution V, but you have to multiply it by how many particles per unit volume you have. And then if you do the integral over all R and R prime, you have the total potential energy. Okay?
Oh, so it's, yeah, okay, I see. So it's basically this gives us the sum of the potential energy. Of
Yes, exactly. Right. Exactly. Now, what I wrote here is a classical expression. Notice that I don't have any hats. Now I want to turn it into a quantum mechanical operator. How do I do that? Very simple. Put the hats, okay? But notice that this V of R prime is just a function. Okay? This is not an operator, it's just a function of R and R prime. It's actually a scalar function, right? Which describes some potential energy of two particles. But now, this rho hat, I know how to write in terms of psi and psi dagger. Okay? So let me start from here and plug in the definition of the rho hat in the second quantization language. Okay? And this is what you get. Just to leave this here, this definition, the density operator. Okay, so if I plug it into here, I get that the interaction can be expressed as 1/2 integral dr integral dr prime. And now notice that I'm doing some reshuffling, and there's a reason why I want to write it like this. Psi dagger of R, psi dagger of R prime, V of R and R prime, psi of R prime, psi of R. Okay, I wrote it in a funny way, okay, but there is a reason for it, okay, and in fact, so this V of R prime, as I said, is a C number, right? It's just a function of R and R prime. So in fact, we could have shifted it anywhere we like, right? It's just a number. Now, these rows are psi dagger psi. And notice I wrote it like this. So this combination, psi dagger of R prime, psi R prime, is rho of R prime. Psi dagger of R, psi R is rho of R. But I wrote it in a funny way, right? Because in order to get from here to here, I must use some commutators, right? It's not trivial, right? So, let me stress. So, let's know, for the time being, let us forget about the V of R, because this is a C number. We can put it anywhere we like, okay? Let us just look at the operators. This combination is rho of R prime. But here, when I want to take it and shift it to here in order to get this expression, right? Right? Because rho of R is psi dagger R, psi R. Okay? Am I allowed to do that? So, okay. So in fact, I'm allowed to do it, but I have to keep track of the commutator, right? And the commutator is going to give me something in general non-trivial. Okay? So why am I writing it? I'm claiming that for our purposes, we can always write it like this, because the correction that we get from the commutator is going to be something that will just give us a shift of the energy or some reference state that is not playing a role in the interaction, okay? In other words, we want to extract from the interaction only the part that has no vacuum expectation value. How do I know that it doesn't have a value? It doesn't have a vacuum expectation value because I have two annihilation operators on the right. Okay, so this V, the way I wrote it, if I apply it on the vacuum, I get 0. Okay? So this is called, we'll come back to it actually later, but this form of writing a two-body operator is called a normal order. Normal order is a way of rearranging the operators so that all the annihilation operators are on the right. Therefore, it doesn't have a vacuum expectation value. Okay? So I'm saying that if you have a general set of A daggers and A's, okay, with different indices, okay, 1, 2, 3, doesn't matter, okay, this thing can be transformed into a normal order plus a correction that depends on the commutators. The normal order is to take all the annihilation operators and shift them to the right. Okay? And because of that, it will give you 0 when it's applied on the vacuum, and therefore it will have a 0 vacuum expectation value. Okay, so I can also write it in fact like this. Okay. Okay, so the reason we want it is if you're talking about interactions between particles, there's no meaning to a value of this in the vacuum. The vacuum just have no particles, so it has no meaning. It may give you a number that is shifting your reference, your 0 of energy, right? So we actually want to subtract it, okay? And therefore, we'll keep this form, okay? But you have to remember it's not identical to this, okay? By the way, I forgot, or maybe I already mentioned it, if I want to generalize these commutators for a continuous variable, then this Kronecker delta changes into the Dirac delta, right? So for example, this for bosons is a delta, the Dirac delta of R minus R prime, and for fermions it's the same work but with anti-commuters. Okay? So with this you can verify what is the difference between this and this, but that is the form that we want to put. Okay? So once again, what is the format? The format is that you have, we wrote it particularly in the basis R, the coordinate basis, because that's the natural thing. We started from something we know from classical mechanics, and we quantized it, right? And the form is that you have some number or matrix element, if you like, that relates R and R prime, but you have 4 operators, 2 annihilation and 2 creation. Okay? So in this way it's written in the R basis, which is very special, and sometimes it's not convenient, right? Because the eigenstates of the particles are not in real space. They can be, for example, in momentum space, or they have some other quantum numbers. Okay? So we want a more general form, and the way to do it is exactly the same as what we did before when we go from lambda to mu, just change of basis. Okay? Just use the same formulas for change of basis. I will not go through it. Let me just write the final result. And this will be the most general form of a two-body operator. Okay, so let me write it here. Actually, let me call it O2, not even V, because it's okay. It's general two-body operator. It's going to be like that. We sum over not 2 but 4 indices in general. Let me call them mu, mu prime, lambda, and lambda prime. And then we have a matrix element, which I'll define in a minute, with these 4 indices. And then we have a mu dagger, a mu prime dagger, a lambda prime, a lambda, okay? And what is this matrix element? Oh, mu, mu prime, lambda, lambda prime is something that if you want to relate it to this, where it comes from the change of basis. The change of basis from the coordinate basis to some other quantum number involves the wave functions, the single particle wave functions. So, okay, I'm just reminding you that psi of R, this is how I got it. Psi of R can be represented as a sum over lambda of some phi lambda of R, a lambda, right? This is, we already saw it, where phi lambda of R is just the wave function in real space representation. Okay? With this definition, the matrix element is, let me just check if I kept track of the factor of half. Okay, to be on the safe side, let's put it here. Okay, this is just a factor of half that prevents double counting. And now what is this? It's an integral over R and R prime of phi mu of R, phi mu prime of R prime, phi lambda prime of r prime and phi lambda of r. Okay? And then if you know the wave functions, you can calculate it, and the result, you integrate over space, okay, and everything here is just a function of r, just an integral. The result will depend on, generally, on 4 indices, okay? And the result may contain a delta of mu and lambda, or it may contain some restrictions, it doesn't matter, but in general, you can have some complex number here that results from this integrals, okay? All right, so that's the most general form of a two-body operator. And let us interpret what it actually describes. It's actually very simple. It describes a summation over many possible processes where you always take 2 particles at states lambda and lambda prime and annihilate them and create new particles at the new states mu and mu prime. Okay? And the number up front, which is just a complex number, describes the amplitude for such a process to contribute. That's what it describes. Okay? So you can actually represent this by a diagram, just this term, okay, each of these terms. You can think of it as, in a pictorial way, as follows. You have some 2 particles at states lambda and lambda prime. They collide with each other. Okay, the picture is not in real space. It's in some abstract space, but they are colliding with each other. Here you have some junction, if you like, that represents this coefficient, okay? And they come out with new quantum numbers. They're not necessarily mu, because mu can be equal to, I mean, some of the indices can be the same or different. You sum over all the possibilities, right? But in general, this is what it describes. In the most general thing is that you have summation over collision processes, okay? And the collision is in some abstract space. It doesn't have to be real space. But an example for that, suppose you have a free gas of free particles, okay? That without the interactions, they would be just, they have just kinetic energy, and their quantum numbers are wave vector, right? And momentum is a good quantum number. But now you have an interaction and you insist on writing it in this basis, okay? What it will describe, because of the interaction, you have to allow for collision. You take 2 particles at momenta P1 and P2, they collide and they come outside with new momenta. Now, actually, for this case, if you know that the system is translationally invariant, and if the interaction only depends on the distance between particles, what can you say about the momenta, if this were really momenta? They would be restricted by momentum conservation, right? And in fact, that's what comes out for this particular problem, okay? So first of all, let us just look at this. This is the most general thing. And in order to see what it gives, you need to calculate this integral, okay? And the result may give you some restrictions on the indices, okay? All right. So let's in fact take this example that I just mentioned. Okay, this was completely general. Now I can erase this. So I'm giving you now an example for a physical problem that you want to be able to deal with using this formalism. And that's the problem of electrons in a metal. As you remember from your undergraduate studies from solid state, a metal is a state of matter that is kind of boring because it's well described by a free gas of electrons, right? Which are, and electrons are fermions, okay, important to remember. So, and you can represent the electronic state in terms of occupations of quantum numbers that are going to be wave vector and spin. Okay? But then, okay, if there were no if there are neutral particles, there's no interaction, and you have a free gas, everybody is happy. But now, unfortunately, or actually fortunately, electrons are electrically charged, right? So it's true that you can, to a good approximation, in a metallic state, there's some magic because of which you can neglect the Coulomb interactions. Okay? Actually, if you just look at the numbers, how strong is the Coulomb interaction compared to the kinetic energy, you discover something very disturbing, that it's not justified just to throw it. It's not small. Okay? The reason why you can neglect it is non-trivial. Okay? But we know that it's true. We know that in a metal, a free or almost free electron gas is a good description of the electronic state. And the Coulomb interaction can be treated perhaps as a perturbation. But in order to be able to treat it in perturbation theory, you need to be able to calculate matrix elements, right? And expectation values. So you want to use the representation of second quantization to do that. Okay? So that's the problem we want to deal with in the next lectures, or one of them. It's electrons in metal. And this is just an example. Okay? So let me write the Hamiltonian is combined of two terms. The first, which I call H0, is just the kinetic energy. Okay, just the free particle part, plus there is electron-electron interaction, and that electron-electron interaction is Coulomb interaction. Okay, so in real space, it has the form that we wrote before with V of R minus R prime is just the Coulomb interaction. Okay? That's what it is. Now notice that here, usually V is some function of two coordinates, but for the Coulomb interaction and many other cases, there is translational invariance. It doesn't depend on the position of the two electrons, only on the distance between them, right? Therefore, we can actually write it as a function of one variable, which is the relative coordinate. Okay, and that's actually simplifying. It's simplifying the description. But let's just leave it here. Now, what is H naught? I want to write H naught already in second quantization. Okay, let's skip the definition because it's kinetic energy. It's just a sum over p squared over 2m. But we can immediately write it in second quantization because all we need to know is, so first of all, H naught is a one-body operator, right? It's just the total kinetic energy. Now, our quantum numbers lambda, what are they for electrons? They are K and spin sigma. Okay, and it's a spin half. Okay, the electrons are spin half particles, so they have two states, up and down in some basis. And this is a discrete index, and this is a generally continuous variable if you have infinite volume. Okay, and so therefore. You can represent the electrons with operators, creation and annihilation operators, that have two indices, k vector and sigma, right? And their meaning is just as usual. These are annihilation and creation for a particle at wave vector k and spin sigma. Okay? Very good. Now, what is the expression for the Hamiltonian? So H naught is diagonal in this basis, right? Because k is a good quantum number. The kinetic energy doesn't depend on spin. Let's for the time being assume that there's no magnetic field. So spin is degenerate, okay? But we have to keep track of it because it's a quantum number. For each k, you have two possible spin states. And another piece of information is, you know that the single particle energies just for good measure, let me write it as epsilon k sigma, although it doesn't explicitly depend on sigma. This is a single particle energy. It's just given by the usual kinetic energy, right? You're familiar with this, and our convention will be that k without a vector sign is just an absolute value of k vector. Okay? Let's keep this as a convention. Okay, great. Now, what is the expression for H naught, therefore? In second quantization, it's just a summation over all k and sigma. And for each k and sigma, you have the number operator A dagger A times epsilon k, right? So you can write it as a sum over k and sigma of epsilon k. Let me just call it epsilon k times A dagger k sigma A k sigma. Okay? This is what it is. That's the Hamiltonian. And the states, okay, we can discuss them later, but we want to write them in Fock space where you have some occupations of all the each of the K state and sigma state. Now, because electrons are fermions, what will be the form of any allowed state? It will have only one particle at each K and each sigma. Okay? So actually, for each K, you can have the two different spins. That's okay, right? Okay, but I'm not writing the states now, just the Hamiltonian. And this Hamiltonian is already diagonal. We know it's all its matrix elements, right? So any Fock state, we can easily compute what this operator gives when it acts on it, because it's already in the diagonal basis. Okay, so it's trivial. Okay, let me just take 1 minute and then we'll make a break. And now I want to write an expression for VEE in the same language, using the same building blocks. Okay? And actually, this expression, this general expression, can be applied here, where I just have to remember that the lambdas and mu's are going to be, each of them is going to be some K and some sigma. Okay? And I have to sum over all the possibilities, and in principle, I will have, let's forget about the spin for the moment. We have how many indices? We're going to get 4 K indices, right? K1, K2, K3, K4. But actually, that's because of the special problem we deal with, which has this translational invariance thing. It turns out that one of the indices will be redundant, because we have momentum conservation in any collision process. So after the break, I'll show you a quick way of how to write the interaction that will give us the right answer. And later on, today we're just going to write it and not doing anything with it. Later on, after some few more steps, we'll see that we can do calculations with it. Like, for example, the simplest thing we can do will be perturbation theory, just to compute the expectation value to get the first order correction to the energy, okay? And so on. Okay, so that we'll do later. So let's take half an hour break and suggest that we continue. Okay, so let me write the Coulomb interaction. So again, the problem is we have electrons in a metal. It has one body Hamiltonian that is diagonal in momentum space. And we want to start from an expression for the Coulomb interactions. I first start by writing the general expression in real space. Just as we had earlier. Okay, here we have some restriction, R different from R prime. And I want to write it like this. It's R minus R prime, rho of R row of R prime, where, so this is just the general form of a density-density interaction. However, if it's a Coulomb, we know that the function V is just E squared over R, okay? Notice that I already wrote it as a function of one variable, which is the difference, R minus R prime, because we know that the interaction only depends on the distance in this case. Okay, so V of R is E squared. Okay, just cool. Okay, and here we have a density operator, and that's actually where the operator form comes from, right? So we want to use second quantization to express it, and we notice that real space, the coordinate, is not a good quantum number, of course, because the states have a quantum number k. The spin, on the other hand, is just nothing depends on it, so it's just a free index, and we can maintain it as a good quantum number, okay? So now I want to write, first of all, an expression for rho of R, the density operator for electrons, in second quantization notation. And before, remember, I defined it as just psi dagger R, psi R. But here we have another degree of freedom, the spin, right? So we can convert from K space to R space. This is just change of basis. But the spin remains spin, okay? And therefore, the real space creation and annihilation operators have two indices, R and sigma, okay? So what is going to be the expression for the density? It's a sum over sigma of psi dagger R sigma psi sigma, okay? Right, so these are the operators that describe the creation and annihilation of an electron with spin sigma at point R. Okay? And when we look at the density, we need to sum over the two spin states. If I write it more explicitly, it's psi dagger psi up plus psi dagger psi down. Okay? Well, these are at the same R, of course. Notice that similarly I can define here spin operator. What is going to be the spin? The spin operator it's generally Pauli matrix, exactly. Right, and specifically, for example, SZ, because the choice of basis for the spin is in the Z, SZ direction, it's going to be psi dagger psi up minus psi dagger, maybe up to a factor of half or something.
Can we have like mixed values of up and down?
What do you mean by, yeah, you can have, of course, if you look at the operator for sigma x, sx and sy, there will be, right?
I mean in the row, like in the density matrix.
No, so that's the thing. That's exactly the thing. Density, just the density is just counting the number of particles per unit volume. Okay?
Only trace.
So it's just the trace. Okay? But it contains a trace over the sigmas, right? Because at each point R you can have an operator. This, if you like, this actually can be defined as density operator only for spin up, and this is for, okay, so you can define partial densities, okay, which have a well-defined spin.
But I find in other classes that the density matrix can have a non-trace.
The density matrix in general, but in case of spin, okay, just the density of particles. It's not, density matrix is a very general mathematical term. Here we're talking about the density operator, okay? So it's diagonal both in space and in spin, okay? Very good, and it has a physical significance in the finite expectation value. Okay? All right, so this is the density operator, but and it's represented in terms of psi and psi dagger, and these guys can be represented in terms of the operators in K-space. But before we do that, I want to do one more step. Let's look at this expression. And I want you to notice that because, just forget for a moment about the quantum mechanics thing, we have here a function of r prime, a function of r, and a function of r minus r prime. Now, if I just look at the integral over r prime, notice that what we have here, so let me just look at the integration over r prime, okay? This guy depends only on r, so I could bring it here, right? Now what is the mathematical definition of this object? This is a convolution, right? And so in fact, here I have one way to interpret this expression. I have an integral over a product of rho of r and the convolution of rho with v. Okay? Now in Fourier space, this gets a very simple expression. Let me now define an operator that I call rho q, and it's nothing but the Fourier component of rho of r. Okay, so it's actually defined as integral over r, rho of r. And of course, no, sorry. There's no spin index, it's density. Okay, density just depends on r. Sorry, so it's this times minus I dot q. Okay, this is the Fourier component. The q Fourier component of rho. So that conversely you can write rho of r as a summation over q of rho q e to the I q dt. Right? This is just the inverse transform. And okay. Good. So let's isolate this definition. And now let us use this Fourier representation by noting the fact that when you have the Fourier transform of a convolution is the product of Fourier transforms. Remember that? Okay? So it turns out if you rewrite this expression in Fourier space, you get the following result. VEE is there's still a factor of 1/2, and let me here put a factor of 1 over volume, where omega is the volume of the system, okay? And then I have sum over Q of VQ rho Q rho minus Q. Okay, now here I owe you an explanation. So first of all, this just comes out of the algebra. Okay. Okay, because you can rewrite this integral as the zeroth component Fourier transform of let me see, so yeah, it's the zeroth component, Fourier component of V times R, the convolution. And this is what you get, okay? I think next tutorial, Sar will do the calculation in more detail, but this is the result. And there's one important thing that I wanted you to notice. Notice that here I got, so first of all, what is VQ? It's the Fourier transform of V of R. Okay? So this is just the definition. It's the Fourier transform, so I'm writing it like this. Just like what we defined for rho, okay? And it's defined in this way, and that's why the normalization gives you a 1 over volume. But it's a matter of definition, okay? We could put the 1 over omega here, but let's leave it like this.
Isn't it supposed to be V of 2Q?
No.
Because
No, this is a Fourier transform.
no, I mean in the VE expression, because
Why?
like
No, there's no
Oh,
2Q. No, it's just a Fourier transform. Okay? You have to, the details Sar will do, but actually, if you just replace, so here I have an integral, I have a double integral in space, and each of the functions here I can replace by its Fourier transform, and then I'm going to get, there is going to be a delta function that gives you, in the end, just a summation over 1Q.
yeah, and then R goes to Q and alpha goes to
Let's
minus
not
Q.
go through the calculation because it's
Okay.
simple. Actually you can work it out as a homework, but it's a standard calculation. Okay, but that's what you get. Now I want to stress. Notice that here I have a product of rho of Q and rho of minus Q. What is the relation between them? Remember that rho of R is density operator. It's a Hermitian operator, right? It describes a physical, something of physical significance. So rho of R is equal to its dagger. It's Hermitian. For that reason, what can we say about rho Q?
Rho Q equal to rho minus Q dagger.
Exactly, that's right. And we saw that already that for any any Hermitian field in real space, in Q space, has this property that rho Q dagger is rho of minus Q. So in fact, another way to write this expression is, which is completely equivalent, is sum of Q. VQ is a function. Notice V of Q is just a function of Q. It's not an operator. And then I have, if I just change the order, okay, and that's again correct up to an overall reference state that has vacuum expectation value, blah, blah, blah. But you can actually, no, you don't even have to do that because there's a sum over all Q, right? So for every Q, there's a minus Q. So just exchanging between these is just changing the order of summation, okay? So you can write it as, okay, this is equivalent. Notice that this is a very suggestive form. It's very compact. And what does it actually remind us of?
Distribution, like partition function. Because it's all these.
No, these are all, these are all operators, right? They're all, right? So they're sorry, maybe I forgot. These are operators. So if you look at the form of this, it describes a term in the Hamiltonian that has the following form. It's like written in some diagonal basis. Okay, there's like one quantum number Q. There's some function of Q, and here you have a rho dagger rho of Q. What does it remind us of? If for some reason I could interpret rho of Q dagger as creation of some particle, this would be a free Hamiltonian, right? It would look like a one-body term. And that's actually, we'll come back to it because it's actually not generally true that you can interpret rho Q as creation or annihilation of a particle, but in one dimension, for a particular model, you can do it, and we're going to use this fact. So we'll come back to it, okay? But it's very suggestive, because if you can do it, it means that you can change the nature of the elementary particles you're working with, and interpret this as a free Hamiltonian of something. Of course, these are not going to be the electrons. Now let us see what is rho Q in terms of electrons, okay? Because it's, this is its definition. It's the Fourier transform of rho of R, and rho of R is expressed in terms of field operators of the electrons in real space. But you can relate psi R and psi R dagger to AK and AK dagger, okay? And of course, keeping track of the spin index, which is just sum over. And what you find, so again, I'm not doing the calculation, it will be in your homework. Okay, so rho Q, if you just plug in for psi R and psi R dagger the expressions in terms of A and A dagger, you get a summation over K and sigma of A dagger K minus Q sigma A K sigma. Okay? And again, how you get it, it's actually a Fourier transform of a product is a convolution. Okay, it's the inverse of what we did before, and that's why you get that actually rho of Q is not just the sum of diagonal terms for each K. No, it's actually a sum over terms where you take, you annihilate an electron at state K and recreate it with K minus Q. Okay, that's rho Q, and rho of minus Q, which is the dagger, will just be the same expression with plus Q. Okay? So if to write it explicitly, rho Q dagger, which is just rho of minus Q, is sum over K and sigma of A dagger K plus Q A K sigma. Notice the sigma is just summed over independently, but in K space, rho is not diagonal. Okay? It describes, actually, what does it describe? It describes processes where you create, if you think of, we'll get to it later, but we think of a Fermi sphere, okay, of which is the ground state of the fermion gas, then the operator rho creates electron hole pairs. Okay, it annihilates an electron at some K state and promotes it to another momentum state. Okay. All right. So now, if I'm taking this term, this interaction term, which is very beautifully expressed in terms of product of rho's, and I just plug in these expressions, I get something that has the canonical form of a two-body operator. So let's write it down explicitly and see how we can interpret it. Okay, so now I don't need this anymore. And there is just one thing that I wanted to mention. So specifically, if V of R is E square over R, the Coulomb interaction, what is the Fourier transform? You remember? I think you have seen it probably in, maybe in electrostatics. Did you see it? First of all, it depends on the dimensionality, but in 3 dimensions, V of Q is 4 pi E squared over Q. This is for 3D. Okay? I don't know if you've seen it, but this can be analytically calculated. Okay, and I want you to notice that it has a singularity at Q equals 0. But Q equals 0 is, what is the meaning of the component Q equals 0? The question is whether we have to worry about it. Okay?
Well, no, because
So okay, right. So actually, let's first of all understand if I'm separating from here the component q equals 0 because it's special and it actually gives a divergence. Okay. If I'm looking at rho of q, this is the general expression. What is rho of 0? If I plug in q equals 0, what do I get? I get this will be 0. So I get just so q equals 0 is I plug here q equals 0 and I just get the sum over k and sigma of a dagger k sigma a k sigma, which is nothing but the total number operator, right? So rho, let me write it down here. Rho 0, the zeroth component, is just n, right? Just the total number. So what is the q component of the interaction? This will now become n squared, okay? Total number square times something that actually, if you are careful and allow for finite volume, it doesn't diverge because q will be quantized, that it will have a minimal value. And what it will give you is nothing but an energy that is proportional to the total charge of the particles square, right? Times something. So what is it? It's like a capacitor, right? It's just the charging energy of a capacitor. So the zero component of the interaction, which in the infinite volume limit it looks like it's diverging, but actually it is just the interaction of the electrons with the total charge of all the other electrons. Okay? But this would be huge energy. Okay? In practice, it will not be infinite, it will be huge, but we don't care about it. Why? Because we're talking about electrons in a material. The material as a whole is neutral, electrically neutral, because there is also the positive background, right? Or the positive ions, if you're talking about the crystal, so it cancels with the positive background, okay? On the average. So in fact, it doesn't contribute anything. Okay, and we don't have to worry about it. We could put here a q different from 0. Okay. Okay, so I'm just mentioning it. This is a detail, but let's now write it down as in the form that I get when I plug in this expression for OQ here. What I get is that VEE is a normalization factor, and now I have a summation over how many momenta? I'm claiming that only 3, not 4. Why? Momentum conservation. It comes out of the calculation. Okay? So in fact, when you plug this in here, you get that there is some delta that eliminates one of the k's. And then I also have summation over 2 spin indices, because each density is combined of terms that are diagonal in spin, but inside the interaction we have a double sum over sigma and sigma prime. So altogether, this is what we get. This is the Fourier transform V of Q, this E square over Q square. And now we have A dagger Okay, actually let me write it, let's see how it's convenient to write it. Okay. K prime plus Q. A K prime. And here I have to put the sigmas. A K sigma. Okay. That's the expression. Box. And let's understand what we got. And again, I'm claiming that each of the terms here in the sum I can represent by a diagram, a diagrammatic description of it, because what does it describe? You annihilate an electron with wave vector k, spin sigma, and wave vector k prime and sigma prime, and recreate them with different momenta. But notice that what are the new momenta? They are such that momentum is conserved, right? Because the total momentum will still be k plus k prime. Okay? So these indices are related by plus and minus of the same Q. Okay? Now, how can I describe this thing diagrammatically? So I'm looking just at this one term. I can represent it as a diagram which describes in a picture the process that I just described. It's a scattering process, a collision, but what happens is actually that you are scattering electrons with momenta k and k prime to k plus q and k prime minus q, and via a thing that takes care of the momentum transfer. Okay, so pictorially you can think of it like this. There is an incoming electron with k and sigma, and it's being scattered. The same electron with the same sigma is being scattered into what is it? K minus q. Okay, so this is k minus q, but the same sigma. But here, how did you lose the momentum? Because you emitted the particle which carries this momentum, this q. Okay, maybe I write it like this because it's a minus q. Okay, and what is this wiggly line describing? It's the v of q. Okay, so v of q, which is just a function of q, what it describes is some kind of probability for exchanging a particle between the electrons. And let me just complete the diagram. Here you have, this is k prime and sigma prime, and it comes out as k prime, wait, no, something is wrong. sorry, the direction of the arrow. This is the correct direction. Okay, sorry, because you emit a particle with Q, and therefore it becomes K minus Q. But here it adds up. The same Q is added and you get K prime. So every point here, every vertex in this diagram describes a collision where an electron emits a particle and momentum is conserved in the process. Okay? So this describes a term in the interaction, and of course the total interaction operator is just a summation of all such processes. Okay? Now what is this particle? So it's a way of interpreting the result. Okay? In a way that involves something that is not in the original Hamiltonian. Our Hamiltonian did not involve any other particles. There was just electrons, right? But we are saying, okay, there is just the fact that charged particles are interacting. There's a two-body interaction that is Coulomb, the Coulomb force. There's nothing else, right? But this picture gives it an interpretation. We can think of it like this. There is a particle that the electrons are exchanging between them, and that's what mediates the force, the Coulomb force. Okay? That's actually the idea also behind high energy elementary particle physics, is that you're saying that all interactions, what we know as fundamental forces, are actually mediated by exchanging some mediator, some other particle. What is this particle then? It is actually the photon. Okay? So, I don't prove it to you. I'm just saying that that's the correct interpretation. And actually, yes?
In the electrostatic is the photon.
Yes, there you are right. You're right, because here Q is just a vector in space, right? So actually, if you want to be more general, you should allow also a time dependence, and then there will be also a frequency, okay? But conceptually, the idea is actually this expression for V of Q that has a Q squared in the denominator is like the static version of an expectation value of creating a photon. Okay, it's actually describing the you can interpret it. Okay, V of Q can be thought of as expectation value of some. Okay, maybe let's call it.
I would say it's the multiplication.
Not A, but let me call it B. Okay, so there is a bosonic particle with creation and annihilation operators BQ, and its expectation value is going to have this 1 over Q squared thing, and that's describing a photon. Okay? Okay, so that's just, but at the moment, I'm telling you fancy fairy tales, but it's an interpretation of this mathematical expression. What we see is that in the process, if you just forget about what happens in the middle, there is a collision between two electrons and via the Coulomb force, and in the collision they conserve momentum, and the reason they conserve momentum is that you have translation invariance. Okay, it's the symmetry of the process, and that's why it constrains the type of processes you can have. So it just comes out of the fact that in real space the interaction is a function of the difference and not of the total coordinate. Okay, not the center of mass. Sorry. Okay. So actually this diagram is very useful for doing calculations. So for now it's just a pictorial description. Okay. And it involves some interpretation that there is an exchange particle, but we later on in the course will see that we can use this picture to draw more complicated diagrams where this electron now can collide with another and create another VQ and so on. And we can systematically do perturbation theory in some regime of approximation, even to infinite order, just by drawing diagrams. Okay? Okay, so, but this is, we'll go to it later. For the time being, this is just a graphic representation of the expression that we got. Okay? Okay, very good. So, I'm already hinting at some things that later on we would like to be able to do. First, one thing that we want to do is this interaction. Obviously, we cannot diagonalize this Hamiltonian exactly. Okay, we cannot solve it. It's not a solvable problem. It has a one-body term and the two-body term, and there is no simple wave function that is diagonal in both representations. Okay? But we'll see that there are two things we can do to make progress. First, we can do perturbation theory, and for that we need to know how to compute expectation value of this and also the variance. Okay? Second thing we can do, and that's only in some special cases, we can find exact solutions, but this can be done in one dimension and exploit the fact that in the representation of the density operator, the interaction rather than the kinetic energy is the simpler form. It looks like a free particle of some sort. But what is this particle? The particle in one dimension, Rho and Rho dagger, are really describing some well-defined excitation. Okay? Not in general, but in some special model. Okay, so this is for later. The last thing I want to do today is to give some guidelines of how actually we are going to do calculations of the forms I'm talking about, which is, for example, to compute the expectation value of such operator in a Fock state. Okay, so I have some general Fock state. It has 10 to the 23 particles. Okay? You can write it explicitly as a product of A daggers acting on vacuum, and you want to apply this operator on it and compute what it's at first sight. It looks complicated. Why? I mean, the calculation is in principle simple, but it looks a bit complicated because we already got a hint of how to work with it. In order to actually get a final concrete answer for what such an operator does, you want to use the commutation relations to shift the annihilation operators to the right? Because this thing has 0 expectation value in the vacuum. If you apply it on a state that already is occupied, you have to reshuffle operators using the commutators until you reach a number plus something that is annihilating the vacuum. Okay? It looks complicated, but it shouldn't be, because notice that we are talking about fermions. Now let us focus about fermions, because we're talking about electrons. For fermions, you know that there is a Pauli principle, right? I mean, this is what comes out. Actually, what is the, how does the Fock state look so now let me erase all this, because I'm going to talk about a more general problem. Okay, so I have some so let's look at the more general problem of interacting fermions. So you have an Hamiltonian like this, and now let's be more general, because, okay, let's not even call it EE, but just interaction, okay? Doesn't have to be Coulomb, and H naught is not necessarily kinetic energy, but there is always a basis where our states, our single particle states are diagonal. Let's call it lambda. Go back to our good old lambda. So H naught in the diagonal basis is just the sum over energies of A lambda dagger A lambda. Okay? The interaction can be expressed as a general two-body interaction, sum over all indices. I'm not even writing it, but for this, we know all the eigenstates, right? What are the eigenstates? The general eigenstates are Fock states of the form product over some lambdas of A lambda dagger acting on the 0. Now notice that here I have only one. Each lambda gives me just one, right? They are fermions. Okay? Now what do I have in the product? I have some set of quantum numbers, and if this Fock state is not necessarily the ground state, so it's not necessarily the lowest energy state, but lambda is associated with a spectrum. There is some spectrum, and there's a hierarchy of energy levels. Let us plot it, okay? So depending on the quantum number, they can be not equal space. There's some spectrum, okay? Now, any Fock state for fermions can be, it has to be something that has only one at each state. So I can have states, okay, I can have some occupation, some others are empty. This is the most general case. However, what is going to be the ground state? The ground state is the lowest energy state. What is it for fermions? It's occupying all the lowest states, right? And in fact, so if you have a well-defined number of particles, if you work in the canonical ensemble, you have n particles, you put them one by one until you're done, okay? Okay, so the ground state, let me call it G0 because it's the ground state of H naught. The ground state is actually something that, let me also give it another name, Fs for Fermi C. Okay, that's just a notation. And what is it? It's going to be a product of it's a product of all lambdas such that epsilon lambda is smaller or equal to the Fermi energy. This is if you are in the grand canonical ensemble, you have a Fermi energy. I'm talking about zero temperature, okay, no temperature, so it's just the same as chemical potential, essentially. And that's it. You have just a product of all these states acting on the vacuum. So the restriction on the lambdas in the sum is that there are all the states for which the energy is smaller than something. Okay, so if this was your spectrum, let's plot it graphically. So there is some states, blah, blah, and then you have a Fermi energy. EF. And the ground state is a state where all the states below are occupied. Very simple, right? Now, if I take an electron from here and promote it to a higher energy state, that's an excited state, right? But this is the ground state, and it's equivalent to a state with well-defined number of particles where the total number of particles is related to E Fermi, right? Okay. Okay, great. So this is the ground state, and it's the ground state of H naught. And now, suppose I want to compute in perturbation theory to leading order the contribution from the interaction. What do I have to do? Just to calculate expectation value in this ground state. But at first sight, as I said, it looks like a complicated calculation because here I have a product of many operators. And for each term in the interaction, I have to shuffle them and all that. Okay? But I can simplify it. I can simplify the description because notice that if the interaction is just a perturbation, so what can it do? When you apply it on the ground state, it only excites it a little bit, right? In other words, it doesn't just excite all the 10 to the 23 electrons, right? What it does is creates there are a few particles that you are promoting from one state to some higher energy state. So it actually, if you look at each term in this sum over indices which gives us the interaction, each of these terms is not acting on 10 to the 23 electrons, it acts on 2 electrons, right? That's all it does. It just takes 2 electrons and puts them in some other places, and it will give you an expectation value if this is allowed process, right? Because, for example, if you want to promote an electron to an occupied state, you get 0, right? For fermions. Okay, so this suggests that we can change our representation in such a way that the empty vacuum will not be important. We are going to redefine the vacuum as the ground state. Okay? We want to define now new operators, new creation and annihilation operators, such that this G0 will now become the vacuum. Okay? Remember, I told you that the definition of annihilation operator is always with respect to a given vacuum. The choice of vacuum is, we have a freedom. Okay? Okay, so to see how we can do it, let's first take the annihilation operator. Sorry, not K. So let's take annihilation operator A lambda for some lambda and apply it on the ground state. Okay, so what is it going to be? Let's write it explicitly. It's A lambda product over lambda primes, which are inside the, so let me actually simplify the notation. Okay, so when I'm writing lambda belongs to F or Fs, okay, this means that epsilon lambda is smaller than F. Okay, that's just the definition. Actually, let me just write it without this, okay, just to simplify the notation. Okay, so this is what we have to calculate. We have a product of all the A lambda prime dagger that are where lambda prime belongs to F, and now I apply an annihilation operator. Okay? Now, I think you can easily see that there are two cases, depending on whether this lambda is inside or outside of this Fermi C. Okay? Let's see what happens if it's outside. Okay? So if lambda is different, does not belong to F, okay? Then what do I get? If it does not belong to F, A lambda commutes with all these operators, right? Actually, sorry, it anti-commutes. But it anti-commutes. There's always, the anti-commutator is always 0, right? Remember, A lambda prime is a delta. Okay? So therefore, we can reshuffle it, okay? And when we reshuffle, each time we exchange 2, we pick a minus sign, right? Right? That's why the anti-commutator. So we pick some minus sign that we don't know how much it is. It depends on the number of permutations we have to make. But in any case, it's just a trivial sign, right? It's either plus or minus, just a number. But this reshuffling will eventually give you 0. Why? Because you can get this all the way to the right.
And then it's equal 0.
Okay, so in other words, let me write it explicitly. You get a product of, you get actually, to be most general, you get a minus to some permutation, okay? This is just a phase factor, and then you get a product of all these lambdas, a lambda prime dagger and a lambda on the vacuum, and this is 0. Okay? So a lambda for lambda not in the Fermi sea is playing the role of an annihilation operator with respect to this ground state. Okay? On the other hand, if lambda is inside, you don't get 0, right? So if lambda, this is, okay, one case is that it's not in F, but if it belongs to F, you get something non-zero. You get, let's write schematically what you get, and again it's up to some phase factor that I don't care about. What you get is just a product of, actually what this will do, it will annihilate only the lambda prime that equals to lambda, okay? Now, because if it's inside F, there is a lambda prime that equals to lambda. It will annihilate this guy, and you are going to remain with all the product of all the lambda primes different from lambda. Okay, and this is some new state. It has one less particles, one less, but it's not 0. Okay, so you see that then, with respect to G naught, if we want to declare it as a new vacuum, we see that depending on whether lambda belongs or does not belong to F, it is or isn't an annihilation operator. Okay? Okay. So this is so just an annihilation operator. The original annihilation operator is not serving as an annihilation operator for this G naught, only in special cases where lambda does not belong to F. Okay? Okay. However, I can now show you that there's another operator that annihilates G naught. Okay? What is it going to be? It's going to be, if I try now to create an electron, a fermion, in a state that is already occupied, what do I get? 0, right? So let us now act on this with here. So if I'm a lambda dagger acting on G naught will give you, let's now again divide to 2 cases. If lambda now belongs to F, what I get is I'm going to get some phase factor times a product of lambda prime different from lambda A lambda prime dagger times A lambda dagger square, right? That's what I get if I reshuffle it until it hits the same lambda. But this is 0, right? So then I get 0. On the other hand, if lambda is not in F, I just create one more particle and I get, actually there is not much, yeah. So in fact there's not much, it's something non-zero. That's what was important. It creates one more particle, okay? It adds a particle, okay, to an empty state. Okay, so now we see that there is an idea here. I can suggest a very simple transformation from the A and the A dagger to a new set of creation and annihilation operators that are combinations of A's and A dagger, such that they will serve as the genuine annihilation operator for this vacuum, okay? So what is it going to be? So let me erase this and just redefine it. So first of all, let me introduce this is a definition of it's a theta function. It's, you know the theta function, right? The Heaviside step function. So this is EF minus epsilon lambda, okay? So I just, for shortcut, I write it like this. Okay? So is it going to be 1 if epsilon lambda is smaller than E Fermi, and 0 otherwise. Okay? Let's write it explicitly. It's 1 for lambda when lambda belongs to F, and it's 0 otherwise. Okay? All right? Okay, that's just a definition. Now, let me now define an annihilation operator, C, and I call it C of lambda instead of A. I use a new notation. And it's going to be let's how shall I write it? Okay. So okay, let's try to, this is just compact way of representing what I told you before. What is C? It's either, first of all, these are either 1 or 0. They are exclusive. Okay, if this is 1, this is 0, and vice versa. And what this gives you is, if I want to rewrite it split like this, if lambda is inside the Fermi C, is an occupied state, then I get only the first term. This is when lambda belongs to F. If lambda does not belong to F, it's the annihilation operator. Okay? But if I apply in both cases, so actually for any lambda, lambda is either inside or outside, there are only two possibilities. And in either case, C lambda acting on this ground state will give you 0. And actually there are two ways to create this, to annihilate this full Fermi C. There are two ways to annihilate it. One is to apply an annihilation operator for a state that is not even occupied, and that trivially gives you 0. Okay? But another way is to try to force an electron, or sorry, a fermion, to an already occupied state, and then Pauli gives you 0. Okay? So, so this is the definition of this for any lambda. This is a legitimate definition of the annihilation operator with respect to a newly defined vacuum. Okay? Now, one thing you want to worry about, we know that A and A dagger obey some anti-commutation relations, right? This is the basis of all our description. What about C and C dagger? First of all, let's write down what is C dagger. So C dagger for any lambda is going to be something that creates particles above this new ground state. From the definition, it's easy to see what it is, because the coefficients here are real numbers, right? So C dagger is a summation of an annihilation operator plus 1 minus theta of creation operator, okay? And that's always creating a new particle. But it does it in two different ways, depending on whether lambda is inside or outside. Because if lambda is inside, so if you have, if lambda is one of these occupied states, what kind of particle is created here? The particle is actually a hole, right? Because it annihilates lambda. Okay, let me write this maybe explicitly. If lambda belongs to F, it's an annihilation of lambda, of the state lambda. If it does not belong, it's a creation. Okay? So, when we apply C dagger on G naught, we get an excited state. But there are two kinds of excited state. One state is when you create, so you can either create an electron, a particle in some excited energy, higher energy state. This is what you get when you apply, okay, let's call it a particle like excitation, because you add another particle at a state that was initially empty. But there is another type of excited state, which is you annihilate one of the states that is already occupied. And then you get a hole. Okay, so you can get, just take one of these and eliminate it, okay? This is called a hole. Okay? Okay, very good. So, so if you rewrite your annihilation and creation in terms of the C and not C dagger, you can treat G naught as a vacuum, and you don't have to keep track of all this long product of states, right? You just need to know whether this lambda is inside or outside, that's all. Energy below or above Fermi energy, okay? And then it becomes very simple because for example, to calculate such a matrix element, so suppose I want to compute a matrix element of the interaction, and I have some two annihilation and two creation, something like that with some indices, okay? Now, what I can do is express the A's in terms of C's, okay? I have to do it carefully because each C is a linear combination of the A and the A dagger, but notice that it's a trivial linear combination because it's, the coefficients are either 1 or 0, okay? So it's binary, but if you can do it, and then you see that you're going to get something that has only 4 operators to work with. And actually all the annihilation ones, if you put them to the left, will give you 0, and you're going to maybe be left with something depending on whether these mu's are occupied or not. Okay? All right. So now one thing that I want to notice, so notice that what I did, here you perhaps see it for the first time, is there is some linear transformation from set of operators A and A dagger to C and C dagger, and the transformation is such that the anti-commutators are preserved, okay? And it's very easy to prove it. I think I don't even need to do the calculation, right? Because you just need to take the anti-commutator of some C lambda and C lambda prime dagger, and now it will depend. And notice that because these two terms are exclusive, so each lambda is either inside or outside, right? So you're going to see that C and C dagger obey exactly the same fermionic anti-commutations. Okay? So the particles that are created by it or annihilated are quasi-particles. Namely, they are not the original fermions, they are some combinations of electrons and holes. And this kind of combination is a trivial version of it, but we'll see later on that sometimes it will be useful to define a linear combination that has a non-trivial superposition. Okay? But it will have to obey some normalization rules so that it can be, for example, a cosine of some angle and a sine. Okay, and here this is an extreme case where the angle is either 0 or pi. Okay, sorry, 0 pi over 2. Right? Okay, so the last thing I want to relate this. Here lambdas were some general quantum numbers. What is it in the case of the electrons in the metal? electrons in the metal, this ground state, this full Fermi sea, is a state where all the K states with kinetic energy below epsilon Fermi are occupied, right? And this is what we call a Fermi sphere, right? So the ground state is really for lambda, for the case where lambda is our K and sigma. We can visualize the ground state in K space, okay? So we can draw some some three-dimensional picture in K space, and in this K space, because the kinetic energy, which I erased it, but the kinetic energy is quadratic in K, right? In the absolute value of K. The condition that epsilon K is smaller than E Fermi is obeyed on a sphere, okay? Or inside a sphere. So this is how it looks like. There is a sphere with radius Kf, right? The Fermi momentum. And everything inside it is occupied, and everything is, of course, again, at zero temperature. This is the ground state, quantum ground state. And now, now if we want to compute interactions, what comes into the calculation is what is the effect of rho Q when I apply the Q component of the density operator, right? This is what comes into the interaction. It's a rho Q dagger, rho Q. So what is rho Q dagger? Oh, I'm reminding you the result we got before. It's a sum over K and sigma of AK plus Q sigma dagger, AK sigma, okay? Now, each of these terms, what does it do? It takes, it annihilates an electron at state K and promotes it to K plus Q, okay? So, let us draw it in picture. Suppose you start from some state. Here, I have some K state that is inside. It's inside of the occupied the Fermi sphere. When I apply such term on it, what does it do? It doesn't annihilate the state completely. It just creates a hole at K and recreates an electron at a state with K plus Q. Now, if this Q is too small, for example, in my picture, such that the state is already occupied, it will give me 0. But if it's not, I can have excitations that take me outside. Let's assume this is Q, okay? So it can create a hole at K and create a particle outside of the Fermi sphere at an excited momentum, okay? Now, of course, for some Qs I will get something, some others I will not. I have to do the calculation. But altogether, what each of these terms is doing is creating an electron hole pair, or what we can call an exciton, right? You can call it that, right? You don't have to. It's an electron hole pair. Okay? And these are the elementary excitations that are generated by applying a density operator. Okay? And some of these terms, if I take an expectation value of the interaction, which is rho dagger rho, right? If I take its expectation value in G naught, I will get some contribution, okay? And the result will depend on the Fermi energy and on Q, okay? Okay. I think this is a good place to stop, okay? It's a bit heavy, I think, but okay. In the course of time, we'll see these things coming again and again, and we'll see how to work with them. But calculations are not complicated. All our point is to redefine always our formalism, our building blocks, such that we don't have to have kilometer-long equations, okay? Okay. So that's it for today. Have a good weekend.